So this next hour, we're going to have 3 presentations by students. I should mention that we were very impressed by, particularly with these 3 student abstracts that were submitted. We originally didn't think of creating a student session, but based on these abstracts, we decided that it would be a nice forum for some student presentations. So I hope you enjoy these 3 talks. After this hour of talks, we'll take another break, which, by the way, does not have food or drink associated with it. We'll have 2 more talks, and then we'll have our poster session. So our first speaker is Blake McShane. Blake is a graduate student in the Department of Statistics at the Wharton School of the University of Pennsylvania. He is a statistical methodologist who creates new techniques suited to the idiosyncrasies of applied data sets in marketing, neuroscience, climate, law, and of course, baseball. Born and raised in Philadelphia, his real passion is the Phillies, and he has the distinction of being born on the day they qualified for the 1980 postseason, going on to win the World Series. He is also graduating this year and is therefore looking for a job. Okay, here you go.
How's it going, everybody? Wanted to thank Mark and Scott for allowing me to speak to you today. Also wanted to thank James and Alex, my co-authors who are not here today, and Shane Jensen, my co-author who is here today. Shane has a poster on evaluating baseball fielding, so definitely check it out in the poster section. So I want to talk to you a little bit today about various metrics in baseball. So obviously, statistics in baseball have a long and storied history, and a lot of that suggests that a lot of people think numbers are really bad and scary. So Harold Reynolds, I don't understand. All of a sudden, it's not just BA and runs scored, it's OBA. And what is it with OPS? Or back in 1980, you press a few buttons and out come the numbers in new ways. Trouble is, most of them don't add much to what we already know. The game of statistics has begun to run away with the game of baseball. I mean, it's not a sport anymore, it's a multiplication table with baselines. Finally, back in the 50s, the greatest menace to big-time sports today is a nonsense of numbers and the stupefying emphasis on meaningless statistics, which is draining the color from competition. But there's another side to this story, right? Numbers are good, and numbers are actually quite old. So if you want to take a minute and read Peter Gavin's recent quote, which opens Alan Schwartz's book, The Numbers Game, talking about all the ways various managers and people have used statistics in the game of baseball, and some of the kind of provenance of these various metrics that go back quite far in time. So, as I said, baseball statistics and controversy over these things are kind of as old as the game itself. And, you know, we have a tendency sometimes to think of this as a product of the Moneyball era, but it's really not. So many of these new statistics are nothing of the sort. So ISO dates from Branch Rickey and Alan Roth's work in the 50s. And Bill James' range factor is quite similar to work by Henry Chadwick in 1870. Regardless of this debate over the history of baseball statistics, though, there's a problem, right? There's a vast number of statistics out there measuring players from season to season. How do you make sense of all of them? I mean, there are just simply too many to really look at. Which of the metrics matter? Which have signal? Which have noise? Which are redundant? And which are redundant? So let's attack it. Let's attack it one way. If a metric were pure noise, what would we expect to see? Right? Players would be completely inconsistent from season to season. There would be absolutely no predictability from season to season. And therefore, if you were trying to predict the player on this given pure noise metric, the best you could do is guess the league mean for that player in a given season. So this suggests a bare minimum that a metric must meet to be even in the consideration set of useful metrics, right? Players must perform consistently with respect to a given metric over time, from season to season. Another way of saying that is when we're trying to predict what a given player will do, we'd rather know about his performance history on that metric than know about the league's performance, right? So this suggests 2 natural criteria for metrics, that this player-specific information trumps league information for a large fraction of players. So if a metric matters, maybe 98% of players, we'd like to guess something based on their performance history rather than based on just the league average. Secondly, it's not enough just to know that there are a large fraction of players that a given metric matters for. We have to be able to identify who those players are. So we want to have large confidence about which players we're using player-specific information for. So I'm going to have one slide on the math of the model. So we're going to assume Yij is the value of a given metric for player I in season J. So maybe you look at some home run rate for all players across all seasons. And we're going to assume that's normally distributed with a league mean mu and an alpha I, which is going to be the player-specific deviation from that mean. So mu is the league mean, and alpha I is the player contribution. And for some fraction of players, we're going to assume that that player contribution is 0. For those players, you're going to want to forecast the league mean as opposed to some player-specific mean. And then for some other fraction of players, we're going to assume it comes from another normal distribution. Finally, we're going to have a parameter gamma that just tells you whether the person's a 0 or not. P1 is going to be our fraction of players that are non-zeroed, the fraction who have their own means as opposed to a 0 mean. And finally, we're going to have season-to-season variation and then player-to-player variation amongst the non-zero players. So this is the model kind of in mathematical terms. Here's the model in terms of a picture, right? You have two groups of players. A group of players who are zeroed at the league mean, and then a group of players who have some variance around that league mean. And this you can think of as their kind of how their talent deviates from the league mean. These guys are worse, and these guys are better. So to get back to what I was saying, there are two natural criteria for a metric, right? Player-specific information trumps league information for a large fraction of players. How do we measure that? Well, we can look directly at our parameter, P1. In particular, we're going to estimate this via a Gibbs sampler. We can look at the posterior mean of that. Secondly, we want to know high confidence about who to use player-specific information for. Well, we can look back at our gamma I, which tell us whether you were in the red group or you were in the black group, the non-zero group or the zero group. And we can look at, we can calculate an average entropy across all players. And this gives us a sense of how confident we are about which players are in the red non-zero group and which ones are in the black zero group. We're going to apply this to player season level baseball data. For hitting, we have 50 metrics across approximately 8,600 player seasons, 1,500 players, and about 25 years of data. Pitching, we have 20 metrics. We fit separately for starters and relievers. Again, 25 years, approximately 1,000 starters, and 1,500 relievers. All our data comes from Fangraphs. So to discuss hitting, here is a plot of that P1 parameter versus the entropy. These metrics are what we would call high signal metrics, and correspondingly, it follows a kind of parabolic shape. These are correspondingly lower signal. To separate out the red and the green, the red and the black, just visually, the red metrics are metrics that if you look at the data, they meet the assumption of our model. The black are metrics that don't. So the model is less reliable for those metrics plotted in black. We decided to just push the model through on them just to see what would happen, but admittedly our conclusions are a little bit less reliable there. Let's zoom in on these metrics, the high signal metrics that I've squared there. What do we see? We see a whole lot of different metrics that all relate to various offense performance. So up here we see things like Bill James' speed, we see a single rate, we see a home run rate, all the way down to the end of this continuum where we see things like batting average. Now, one thing that was of concern is we had 50 different metrics, right? And we were hoping that we could boil this down to a couple of metrics that really mattered, that there wouldn't be a large number of important metrics. As it turns out, this continuum up here of very high signal metrics, 35 of the 50 metrics were up there. So in one sense, that was a little bit disappointing because we wanted some separation, but that's what the data said. However, when you take a look at these metrics right here, you realize that maybe some of them are kind of similar to one another. So obviously, up here we have a single rate and we have batting average. Well, singles are one of the components of batting average. Maybe batting average is largely driven by those singles. So maybe these metrics are very highly correlated amongst one another. So that's one of the things we looked at. We did a principal components analysis, and it turns out of the 50 metrics, there are only really about 7 or 8 distinct principal components. So even though we see 35 very high signal metrics here, there aren't very many truly different metrics. They're highly intercorrelated with one another. Just to take a closer look at some of these metrics, I flagged some of the interesting ones from the upper quadrant of that plot. So isolated power, walk rate, speed, and strikeout rate. What's interesting is, obviously, for some of these, you see quite a substantial overlap in players. Unfortunately, I was only able to fit the top 5 onto this slide, and so you only see some things. So, for instance, Barry Bonds coming up in both places, and you see Jack Cust. But what you'll see is there is considerable amounts of overlap when you examine maybe the top 25 players on a lot of these lists, which kind of fits nicely with the idea that these metrics are really highly correlated with one another. What happens when you go on to pitching? Pitching is interesting because you have a natural set of replicates in the sense that you can look at starters and relievers separately. So again, black are the ones that don't work don't fit the assumptions of the model as well. Red do. That's for starters. For relievers, green don't fit so well, and blue do fit very well. Unlike hitting, where there was a high continuum of high signal metrics and then a kind of big breaking point, here in pitching, there's a much smaller group up here. So let's zoom in on them. What do we see? We see infield fly ball percentage, which doesn't really meet the assumptions of our model. It tends to be bimodal, and it looks really strange. So we'll ignore that one for the moment. But we see real differences for starters and relievers. So for relievers, we see ground ball percentage, fly ball percentage, and strikeout rate. For starters, things like fielding independent pitching, home run rate, ERA, and walk rate. And actually just number of pitches. Obviously, this was a sanity check on our model. If you're a starting pitcher who is performing well, you're going to have a fairly consistent number of pitches thrown from season to season. So this suggests that our model's doing the right thing, at least on that metric. Again, what do we see for starters? Well, you see some really big names up there, and in particular, again, some more overlap. So who do we see? We see, a number of names, and you guys can just have a little look at this. I think the relievers are possibly more interesting. So instead of looking at fielding independent pitching, home runs, ERA, and walk rate, which were the big metrics over here, we're going to zoom in on these 3 up here, and I'm also going to add walk rate because if you were to extend this plot out, walk rate sits right about there. What do we see? Strikeout rate, we have Brad Lidge leading the way, who probably isn't doing so well this year, unfortunately. But if you add if you add the current season of data, it would be interesting to see where he goes on that. But again, considerable overlap. And what's interesting, I think, with the relievers is you see between ground ball percentage and fly ball percentage some strong amount of overlap. And usually the people who are, obviously since ground ball percentage plus fly ball percentage plus line drive percentage must sum to 1. And since our model tells us that line drive percentage is essentially complete noise, that you can't really see much signal in that, you see the guys who are correspondingly high on ground ball percentage be correspondingly low on fly ball percentage. So right here you have a 66% fly ball percentage compared to a league average of 45%, which leads to a correspondingly diminished 18% fly ball percentage compared to a league average of 35%. So in conclusion, what do we see? Well, for hitting, a large number of these metrics have signal, 35 out of the 50 of them, but they're highly correlated with one another, and they're also related to kind of traditional notions of performance. This makes us wonder whether Seymour Sewaff's quote was correct, that there are all these new metrics, but what do they really add to what we already know? How about for pitching? High signal metrics varied quite considerably between starters and relievers. For starters, these high signal metrics tended to be more measures of overall performance, whereas for relievers, they related to specialized roles. So, it's more common to bring in a reliever to face maybe one or two batters, and it might make sense that these measures that matter are more specialized. Thank you very much for having me. If there are any questions. I'm sorry? Sure. All right. So basically, there's one of the parameters of our model is whether your mean is the league mean or whether you have your own mean, right? And our model tells us with which probability you have your own mean and with which probability you have the league mean. So call that P. You take P log P plus 1 minus P log 1 minus P. And then you do that for all the players and just average it together. And what you find is that, so for a case where P is either 0 or 1, the entropy is 0 because there's no randomness. And it's maximized at P equals 1/2, where there's the greatest uncertainty because we really have we don't even have any sense whether you're 0 or player specific.
Thank you. James? Yeah, for the betting measures, we did the principal component came up with 7 factors. Were the factors interpretable? Like they mean something?
I think so. The first couple were. It's always tough to interpret them, especially when you have 50 different things. The first one or so probably related to kind of consistently hitting things like singles or overall batting, and I think the second big one was related to things like power, so home run rates, ISO, OPS, things like that. So there was some interpretability. Once you get down here, it was more difficult to kind of get a sense.
OPS has to be the best measure that you have.
Pardon?
OPS is the best measure of offensive ability.
In what sense? So our model certainly agrees that it's a very, very high signal metric. In terms of, if you're trying to, I mean, in what sense would you say it's the best in trying to... Sure. Yeah, so it wasn't, we weren't specifically trying to do this in a predictive sense of other metrics, but how consistent were players on a given metric from season to season, which is why I think this is, as I said, this is a minimum, at the very least, it's a minimum threshold.
Last question, Tom.
Just wondering if there are any distinguishing characteristics of the players who were best predicted by the league mean. I mean, what types of players were those?
So typically for hitting metrics, it was bad players. And good players usually, if you went down the list of all players and looked at the top, say, 100, among the top 100, almost all of them were above the league, substantially above the league mean. So let's look at ISO. You have McGuire at 32 compared to a league mean of 14. That was a fairly typical pattern. For pitchers, actually, it was much more, there was no kind of consistency like that. There was no clear identifiable consistency.
All right, let's give another hand to